Welcome back to the Grinding Doc video series. In this episode, Dr. Jeffrey Badger responds to an inquiry from a shop that didn't have much luck with ceramic abrasive. They would like to know if they are doing something wrong.
One of the reasons ceramic abrasive hasn't had the success that maybe it could have had is because people don't use it properly. Typically, people are grinding with their regular aluminum oxide wheel. Salesman comes in and says, try this ceramic grit wheel. They stick it on, they use the exact same speeds and feeds and everything, they try it, they get chattered, they get burned, they say to the salesman, this stuff doesn't work. And the reason is because ceramic abrasive is very tough, so you have to push it hard to get it to fracture. Now when I say ceramic abrasive, we're talking SG, Norton, SG, TG, Cubitron, seated gel, sol gel, sintered abrasive, ceramic abrasive, or microfracturing abrasive. It goes by many names. All those are ceramic abrasive, and basically they fracture in little bits and pieces instead of chunks. So if we're using it correctly, this is what we should see. We should see a worn grit, but instead of becoming dull, it's fractured in little bits and pieces at the tip. So it's wearing, but it's staying sharp. Or if we zoom in, we see little chunks at the tip where little bits of ceramic abrasive have plucked out. So therefore, it's constantly staying sharp. As opposed to this. Now this is an aluminum oxide grit that's become dull. And this can happen to ceramic grit too. If you don't use it right, the ceramic grit becomes dull because the forces are not big enough to get it to fracture because it's tougher than regular aluminum oxide grits. So here's a company I visited about a year ago, and this is the output from the grindometer, which measures the spindle power or the power in the grinding operation. This was a 4-flute operation. We did a roughing, a finishing, a roughing, a finishing, a roughing, a finishing, a roughing, and finishing. And what we can see from the power signal, when we're grinding at very low feed rate, our power signal goes up and up and up, both in the roughing and the finishing. The reason is because the wheel is becoming dull. So we saw this and we said, okay, this is not good. This is typical of a ceramic grit wheel. We need to increase the feed rate. Increase the feed rate, and what we see is the power really didn't go up very much, because our wheel is self-sharpening well. What you'll also see is the slope there of that little dotted line is decreasing because the wheel is self-sharpening. It's not dulling. Cranked it up again, this time in red, and we see almost a flat power signal because our wheel is now self-sharpening throughout. Then when we went even faster, we maybe have gone too far and our wheel is opening up too much. So our optimum is probably around 600 millimeters a minute, or the one in red with an aggressiveness value of about 18. So that gives us a good self-sharpening wheel. And that's pretty typical. Basically, we stick on the wheel, we say, we're not aggressive enough, let's grind it more aggressively. Our wheel starts to self-sharpen, boom, everything is taken care of. So how do we self-sharpen our wheel? There's a number of ways to do it. If we're doing surface grinding or creep feed grinding or plunge grinding, we can take a deeper depth of cut, we can take a faster table speed as we did in the example, or we can take a lower wheel speed. If we're doing cylindrical OD grinding, we can also use a lower wheel speed, or we can take a faster plunge speed, we plunge that wheel into the workpiece faster, or we increase our workpiece RPM. All of those will result in a more aggressive grind, bigger forces on the grits, get those grits to fracture, and therefore we can use that ceramic grit the way it should be used.